Okay, so we did all this. We learned how to do this technique, and we could, write this formula down and do this limit and get this interval. But what does it all mean? So what's the point? So that's the most important thing. What's the point of this? Could you articulate what is it that we did and what's going on here? Why don't you tell the person next to you? Get a partner. What is this all about? So this is a lot more than just a procedure and some symbols to write down in the right order, okay? What's the meaning of this? Go. Okay. Brady, is that you, Lorenz?
Yeah.
Tell me, just get me started here. What's the significance of this, or what's going on here?
So you have a function that you can plug any number into, and then you convert it into a sum of all the numbers from 0 to infinity added up, basically.
So is it?
And you find out where it's converging, which is obviously the negative 1/4 to 1.
Okay, so this function is equal to a sum of numbers.
Well, you make like a sum of, if you were to plug in at x is equals 0 all the way to x equals infinity.
Okay, no, not quite, not quite. So you're confusing n and x there. You're confusing n and x. All right, where's Trista? Is Trista still in the class? Levi.
So what my partner and I said was, is that when we turn it into that power series, that whole summation is a representation of the graph.
Okay, what kind of representation is it?
So it gives, as n approaches infinity of that series, it shows you like all the infinitesimal points of the graph. So it's like, as we add up all those values, we'll get points that represent.
Okay, so you said the same thing, adding up a bunch of values. Are we adding up a bunch of values? What is this, guys? Summation of what? It's not, these aren't. So see, okay, so let's use this form. Everyone write down, when you see this, what does it mean? Write it down. So see this, think what? See this, think what? Write it down. Everyone write it down. What are we summing up? What are we summing up? Junial. Junial here? Ah, what'd you do? Tell me. Why do you continue to sit there then? So you can't, so every lecture you sit there and you can't see the screen. Okay, talk to me after class, okay? Ricardo. Okay, let's have a conversation very soon. Okay. Yeah, sure. Ricardo.
It's a sum of functions.
Okay, tell me. What did you get? So when you did this exercise, what did you get?
Negative 5x.
Negative 5x.
20x squared minus 16 times 5x to the third.
The 80.
I'm not sure.
Okay.
I didn't do the rest, but dot, dot, dot.
Yeah. Let's do one more. And we got the next one. 320. Okay. So what is this? He said a sum of functions. Okay, that's true. So when we write this function as a series, we're really doing what? Right. We're rewriting it as a polynomial with an infinite number of terms. So we get a new function, but that function, in order to exactly match this one, we have to keep adding terms forever. Okay, and this are the first, say, 4. If we keep adding those terms forever, we get exactly this function. So a power series ends up being a polynomial, like an infinite polynomial representation of the original function. Okay, but there's more to this. There's more to this. Who wants to add? So we've got an infinite polynomial representation of this, but what? Christiana or Alec? Sorry. It only works for these x values. It's only going to work from this very. Is that what you're going to say? Yeah. Okay. It's only going to work for x values between negative 1/4 and 1/4 because if x were outside this range, what would happen? This would be divergent, right? It wouldn't. This series for any x value outside of negative 1/4 to 1/4, this would be a divergent series. So it can't possibly. It's just gonna blow up. So it's not. It can't reproduce h of x. So it's only going to reproduce h of x for these values of x. Yes, Corey?
What makes this notation more useful than, say, the function notation?
Because so polynomials are really nice to work with. Yeah. So and it's kind of the idea, and we're going to see this in the next topic, that any function can be replicated with a polynomial. And we're not seeing that yet. We're seeing a very narrow class of functions. But then polynomials are they're like really easy to work with. Like derivatives, integrals, super easy. They're just very user friendly. Okay. Whereas like a rational function.
So if you wanted to take, say, the derivative of that, you just take that.
Yeah. So any derivatives of this or antiderivatives, we could get estimates of those functions as well by doing the derivative or antiderivative of this polynomial. Okay, does it make sense? So what we've seen is like Friday we started building some where we needed a derivative or antiderivative to actually build it. So let's do another one of those examples. Let's finish the example we started last Friday. Any more questions about the quiz problem or what's going on here? Okay, so let's find that example. Where was it? It was this one. So we were working on this one, and we said we want to write this as a power series, and that doesn't look anything like a over 1 minus r. But what is a function in that form that might help us to get that? And did we call it f, or what did we call it? In your notes, was it f? So we need a similar function f. Something of the form a over 1 minus r, or something that's going to then help us get this. So what did we say? We said what could we find a power series for that'll help us get this? We started simpler than that. So yes, we want to do. So we know. So we see that 1 minus x squared. We say, oh, that looks like a lot. So can we now relate something like this to natural log? That's the point. So in general, does this relate to natural log, and how? So this is what of the natural log of 1 minus x squared, or essentially what? It's the derivative, right? So if we could do the antiderivative of this, we'd have natural log of 1 minus x squared, and these factors we know we can just tack on x squared. All right, so we want to do antiderivative of this, but then we think about all our techniques for antiderivative, and we say, this isn't a straightforward antiderivative. How could we make it a lot simpler? So what could we make the numerator so that we have a straightforward antiderivative without? Remember, by undoing the chain rule, right? If it's antiderivative, undoing the chain rule, we would want an x to the first term. So here's where we started. So we'll write out this one, and we know this will be n equals 0 to infinity. So does all that logic make sense? Ask me if you're not sure. Does it make sense? Go ahead and ask if you're not sure.
No, I get this.
Okay.
Why wouldn't you choose -2x at the top? Or is that skipping a step, or is that just wrong?
Yeah, you could do that. Yeah, you could do that. So that's going to make, so it's like it's a trade-off, right? Because so that'll make this initial series more complicated. You'll be injecting kind of more elements into this, and then it might be a little easier down the road. Or you can have it easier now, and then when you have to include that factor when you do the antiderivative. So it's just pick one or the other. So both work. It's both work, yeah. So yeah, if you want to start with -2x, yep, you could do that, and then so you guys want to do that? We can do that. But so x over 1 minus x squared works just as well, but let's do that. So -2x. Okay, so then -2x. I'm sorry? Yeah. No, it's the derivative of just this part of it. It's the derivative of natural log, derivative of that. So we're just thinking about what power series can we know that we can write down that we can bridge our way back to this. That's the idea. So -2x times what? X squared to the n. And so we could rewrite that as -2 times x to the what? 2n plus 1. And then I recommend that you keep track of this form. You keep track of, so this is still f of x. We're still at f of x here. Haven't done anything to it. And then write down several terms. So we're gonna have -2 what? -2x first. And then -2 x cubed. Am I doing this right? Are we good? You agree with that? A couple nods. Okay, good. So now we've got -2x over 1 minus x squared. And what are we going to do to that to get what we want? We're going to do antiderivative, right? We're going to do integral. And when we do integral, it's going to equal, well, that's going to be our natural log of 1 minus x squared. We set it up to be exactly that. Okay, and then and we're going to do it in all the forms, right? So we're going to do antiderivative of this. So antiderivative will be negative 2 times x to the 2n plus 2, but then all over 2n plus 2. And now let's do these one at a time. And then we'll check this way, right? So we're going to work vertically like this because we can definitely trust our antiderivative of the polynomial, or we should, and then we can check horizontally this way. Make sure our sum notation is correct. So antiderivative of negative 2x. Negative x squared, and this will be minus 2x to the 4th over 4 minus 2x to the 6th over 6. Agree? Okay, so now does this, where are we going to start? We're going to start with n equals 0. Does n equals 0 give us negative x squared here? N equals 0, again, negative 2 over 2 is negative 1, looks like it. Yep. Okay, and then if I put x equals 1 in here, I get negative 2 over 4x to the 4th. If I put 2 in here, I get negative 2 over 6, x to the 6. Looks like it's right. Okay, so now we're ready to write what function j is. What's function j? So what are we going to do now to that to get function j? Times x squared. So I should have, it'd be easier to see. I just wrote. This step is integral fx dx. That's what this intermediate step was. So we did what? Antiderivative. And now this step is multiply by x squared. And now jx equals x squared, ln of 1 minus x squared. And then we're going to multiply this by x squared. Negative 2 x to the 2n plus 4. Right? We just multiply by 2 more x's. It should be 2n plus 4 over 2n plus 2. And then this simply gets multiplied. Every term is just simply multiplied by x squared. So minus x to the 4th minus 2x to the 6th over 4 minus 2x to the 8th over 6 minus 2x to the 10th over 8 dot dot dot. And then again, we want to check this way. We want to check that this series gives us those terms. And it does. So there's the power series for J. Where is it valid? Where is it valid? So we want to do a ratio test. -2 x to the 2 n plus 1 plus 4 over 2 n plus 1 plus 2 times 2n plus 2 over 2 x to the 2n plus 4. So I think the -2's will cancel. When we take so the limit really just, and then how many x's will we have? How many more x's on the top? 2 more x's on the top than on the bottom, right? So 2n plus 6 and 2n plus 4. And then the limit of 2n plus 2 divided by 2n plus 1 plus 2. So now we can evaluate the limit. The limit really just pertains to this part here. 2n plus 2 over 2n plus 4. Limit is 1. So that's the limit part. And then you said we have just 2 x's on the top. And the -2's go away. So this is going to be, so square root of x squared less than or equal to 1, less than 1 is the same as x less than 1. So it's going to be between -1 and 1. Okay, questions on what we did? Oh, yes, we should. But I think, okay, good. So, when x is, oh, sorry, got it backwards here. All right, so when x is, say, -1, that's just going to go away. It's just going to be 1. We have -2 over 2n plus 2. So whether it's -1 or 1, x to the 2n plus 4 is going to make it positive. So really, for both cases, we're checking the sum. I'll do it in red. In both cases for -1 and 1, we're checking the sum. -2 over 2n plus 2, which is the same as -1 over n plus 1. These all have 2's in them. How about this? Convergent or divergent? So essentially, what is this? This is essentially the harmonic series. Adding 1. So when n gets really, really big, adding 1 in the denominator is absolutely meaningless. Essentially, this is the opposite of the harmonic series, which we know is divergent. So just between -1 and 1, not including the endpoints. Okay, any questions? So let's check the graph. So I got it started here. So here's the graph of the original function. Maybe. There it is. Okay, so that's the function, and so you see that it's really only defined between -1 and 1, and so the series is going to, if we did it right, we'll reproduce it in that, actually the whole function from -1 to 1. So what did we get for that? -2 times x to the 2n plus 4. And that all over 2n plus 2. Okay, so let's see. Do I have it written right? Starting from n equals 0? All right, let's see. Okay, so this is just just the first term of this, what, we think of this as an infinite polynomial. If I just take the first term, I get that right there. If I take the first two terms of that infinite polynomial, I get that, the red. First three, okay, it's not, something's wrong. It's getting worse, not better. So do I have this, do I have something wrong here? Is it 2n plus 2? Okay, not helping. What, is this what we had?
Negative 2x, 2n plus 4 over 2n.
X to the 2n plus 4? And it was over 2n plus 2? Okay. Something's wrong. We know what it's supposed to do, right? So the question is, why isn't it doing it? Maybe I'll. Does anyone, we're not going to take a lot of time to try to figure that out. I can do it later. But does anyone see an error that we did here? This is what we got, right?
We accidentally put in because I know we started off with x over some x, but then we multiplied by x squared at the end. Does that have anything to do with it?
That's what makes it plus 4, not plus 2.
Yeah. So I have the function right? That's the function we did. Okay, I'm gonna have to mess with it and see what happened, because I think we like this. This is what we got, and this is what we had. So as we take more and more terms, that red function should be converging on the blue one, not it seems to be getting worse, right? It's getting worse. So I'll have to see if maybe there's something in the way that I'm entering this. Let's just try it a different way here. I'll try -1 divided by, see if this is any better. So is this equivalent? So we had -2 over 2n plus 2, right? And that's the same as -1 over n plus 1. Would you agree? So maybe it likes, no, same thing. Okay, so what's that? Yeah, that's what we got. This is -1 right here. It's going to give it for all x. You know, it'll give it for all x. But it's only giving us. Oh, this is a little different. Let's see. Yeah, I don't know. I have to find out. It might be a glitch in the program too. Okay. Anyway, so you've got hopefully you've dug in and started. You got like I think 4 or 5 of these where you have to utilize derivatives, antiderivatives to answer these questions. All right, so let's just do a little preview here next time. And so on Wednesday we'll start Taylor and Maclaurin series. And what is this about? So really we've only seen functions of the form a over 1 minus r, and then ones that are related to those by derivative and antiderivative, right? So that's a very narrow class of all functions. So that's very restrictive. This technique we've had, it's really important using geometric series and these techniques, but it's restrictive because you can only have very special function or derivative or antiderivative of something that looks like that in order to use that. So Taylor and Maclaurin series, they allow us to write any function as an equivalent power series. Meaning, and this is what we talked about earlier, that any function can be estimated with a polynomial using a Taylor or Maclaurin series. So a Taylor series And so the Taylor series has a center. It's centered about x equals a. So it'll be the best at a, and then as you include more and more terms, it will do a better and better job away from a of estimating the actual function you started with. Okay, so that's what we mean by centered about a. And so this is the form of it. And so what is this? This is the nth derivative. This is the nth derivative taken at a of the function that you're representing. This is x minus a to the n over n factorial. So f n a is the nth derivative evaluated at a. Okay, so what does this mean? This means the actual, so the 0th derivative is just the function, right? The 0th derivative, it's just evaluating the function at a. So it'd be f of a over 0 factorial. And then the first derivative taken at a times x minus a over 1 factorial, etc. Second derivative evaluated at a, x minus a squared over 2 factorial. Yeah. So there was no why about this formula. I didn't embark on that. So why? Let's see. This is about centering it at a, right? So that I mean, so that's I can't say much more than that. That when we're centering it at a, it's like this. This is going to shift a function, right? So x minus a would like shift a function a units to the right. So it's like we're shifting it to center it at a. That's basically what this does. Okay, and then a Maclaurin series is when that a value is 0. So it's a specific case of the Taylor series. Specific case of the Taylor series when you center at 0. So those are really nice. They're user friendly. They're easier because things tend to drop out and become simpler at 0. So we'll do lots of examples and investigate these Taylor and Maclaurin series on Wednesday. And you've got your web work. And so we'll then, so we need to start, so the exam is a week from Friday, and it covers through Taylor and Maclaurin. So keep watching Blackboard. I promise we're going to have written homework. Keep watching Blackboard.
We're just going to do a bunch of problems. Functions in series.
Yeah, the ones where they have to use derivatives and integrals.
Yeah.
Yeah, like probably can get through 2, maybe 3 in 50 minutes. Yeah.
Okay. Sounds good.
Thanks.
2 questions. Oh, for the graph, try doing +3 and then over +3.
This one?
Yeah, but try just oh, you think so. Try this, but instead of this, try -2x. I didn't write it down, but try -2x to 2n plus 3 over 2n plus over 2n plus 1.
Like this?
Yeah. Oh wait.
No. It's an odd function. Ours is even.
I have no idea how to. Well, I have another question, but I'm
Yeah, sure.
a while, so I'll
Yeah.
let them go.
Hey.
I just had a question about the quiz.
Yeah.
So when you're setting up the equation, we had something like